So we'll start a new topic. We'll talk about Gaussian process regression. And Gaussian process is somewhat simplistic, and there is nothing complicated about it. So maybe it's helpful to connect it to something that you might already know, a random walk. So imagine you have a random walk, and you know it starts at zero. And let's say we have time axis and the random walk here, and let's say it starts at time zero. You start random walk starts at zero. So let's say we denote that x is the random variable that follows this random walk, and let's say the step of the random walk is follows normal distribution. So every time you make a symmetric step, okay. So and if you try to draw a realization of that, it's going to be something like that. So every time you just add a random number, so x t plus 1 equals x t plus epsilon, and epsilon just follows normal distribution, and we're just going to set it mean and some variance sigma squared. Okay, so what you see here is one realization. And if you try to do it once again, if you run your computer simulator once again, you're going to start at zero, and let's simulate it second time, and you'll see different line, but so it's going to be something like that. Okay, there are a couple of things we can say about this random walk. So one thing is that the further you are away from this point zero, the larger the variance is. And the point zero is where you knew what the value of the random walk was, and the further you are away from this known location, the larger variance become. So that's one observation. So variance depends on the distance. And another observation, and actually in this case, variance is relatively easy to calculate. Or standard deviation is going to be square root of t. Sigma is the standard deviation of x, and actually x, we're gonna xt, right? Because we're gonna index it with this variable t. And another observation is that if you take 2 points, if you take this point and this point, they're going to be correlated. And the closer they are to each other, the more correlated they are, just because the next one is just an increment of the previous one. And so by the nature of the definition, they are related, and there's a covariance structure. Okay. And essentially here, not so I did discrete time, but now you imagine that delta t goes to zero, so your time step goes to zero, so you basically have those smooth lines rather than the jerky zigzag lines, but nothing changes. The same intuition holds. The closer you are to zero, the less the variance is, and the closer the 2 points to each other, the more they are related, the more correlation structure there is. So random walk is just a specific example of a Gaussian process. Gaussian process is just a little bit more general thing than random walk, but the same intuition will hold. So as far as you remember that the correlation depends on the distance, and basically every time you run the random walk with a Gaussian process, you have a curve. And you can think of a Gaussian process as distribution over those curves, or a sample of it from a Gaussian process as a curve. So it's an instance of this generalization of the random walk. So to understand the Gaussian process, it's a prior over random functions, and you can calculate the posterior given the data, and you can use it for spatial analysis. You can use it for computational experiments, and that's probably the two most successful applications of Gaussian process. So computational experiments, modeling computer codes, modeling physics simulators, modeling agent-based simulators, and analyzing the spatial data. Most of the spatial models that involve continuous variables will involve Gaussian process in one way or another. And outside of the spatial data in computational experiments, Gaussian process is used as well. It's closely related to spline interpolations. It's also closely related to kernel techniques. We're not gonna go into that, but there is a Gaussian process textbook. There are actually a couple of them. So the one is written by Bobby Ramsey, which is more recent one. It's more written using the language of statistics and more geared towards statisticians and engineers. So he talks a lot about computational experiments there, for example. And another one is also called Gaussian Process, written many years ago and mostly written using the language of computer science. So either of the books are great reads, depending on what your preference in terms of the notations and language, and what are your applications you're working on. So the book by Bobby Gravis is the one I would prefer, just because of the way it's written and the examples are given, and it's more modern, so he has more new stuff in this book, which is quite relevant to a lot of the applications. And he also has R packages behind most of those things that he talks about in the book. All right, so let's move on, and let's talk about Gaussian process. And so Gaussian process is defined essentially by this correlation structure between 2 points. And correlation structure is defined by what is called the covariance function. And covariance function, you give me 2 points on the line, and the covariance function tells me what is the covariance of those two observations. And the simplest covariance function is given here, and it's not only the simplest, it's also quite powerful. So don't be tricked by its simplicity. It's quite powerful, and it's quite often used in real applications. So the fact that it's simple doesn't mean that it's a toy covariance function. It's actually quite useful one. And here's the functional form. You take the distance between 2 points, x and x prime, and you square this distance, and then you take exponent of negative square. So we're gonna call the distance equals to x minus x prime, and so let's say that's gonna be distance squared. So, and if you look at the distance and the covariance function, it will have a form like this. Okay. And since the distance is strictly, not strictly, but it's a positive, non-negative number, so then we know at 0, it's actually going to take a value of 1, so that's going to be the largest value. And as distance increases, as it becomes larger and larger and larger, the covariance becomes smaller and smaller and smaller, and so basically as distance goes up, your covariance between 2 points that are far apart, d far apart, goes to 0. Okay, so that's the property that we want. The closer the point to each other, the more they are related, the higher the covariance is, and the further they are away, the weaker the covariance is. So looks like it fits what we need. And so let's do some simulations. Essentially, so one thing to keep in mind is that the matrix. So if you take some observations x1 through xn, so just any numbers on the real line, and then you calculate the covariance matrix for those using this covariance function, right? So basically, you'll have to so you calculate sigma. And ijth element of the sigma is the covariance of xi and xj, calculated according to this covariance function here. All right, so if you calculate such matrix sigma, then this matrix sigma is going to be positive definite, so it will satisfy the criteria of a covariance function. So for any x transpose sigma x is non-negative number whenever x is a non-negative vector. All right. Now, so let's see how the data generation mechanism works. So we explained how this random walk generation works, so we can simulate those random walks. Now let's see how can we generate samples from a Gaussian process. So let's say you take a whole bunch of x values, so just any numbers on real line, and then so you take a whole bunch of x values and then you calculate the covariance function. Ijth element of this covariance function is just the covariance function applied to xi and xj. And then what we want to do, we want to draw an n-variate realization. So now we have some variable y that follows normal distribution centered at 0. And the covariance function that was calculated from xi and xj pairs. And let's do that and let's plot it. So we're going to generate 100 samples. And x is just the sequence of numbers between 0 and 10 of length n, of length 100. And this distance function calculates the pairwise distance between those x observations. So it's going to be a square matrix, n by n matrix. This is n by n matrix. And then what we do, we just take exponent of negative d, plus we have this diagonal element filled with a very small number, 10 to the negative 16 for my machine. So it's essentially so we avoid the problems with inversion of the matrices. It's a computational trick that makes things easier, but it's just it's a nuance. So all right. So and now we have the covariance function, and mean is 0, and we're going to use this RMV norm. It's a function that allows us to draw samples. We're just going to draw one sample from this multivariate normal, and you remember the sigma matrix is of size 100 by 100 in this case. So it's a 100-dimensional normal that we are going to draw, and that's it. So we generated a finite realization of random function on the Gaussian process prior, and we generate with a specific covariance structure. So the covariance structure was exponenta of negative distance. And let's visualize it. So we're just going to plot our x, which is just a sequence of numbers between 0 and 10. And then y is our sample from the 100-dimensional multivariate normal. Right? Here we go. Here we go. So it's nice looking random function. So it's just one realization. So what we see here is one realization of Gaussian process. Okay, so what are the properties? Let's look at this. So it ranges between -2 and 2. That makes sense. We know that our covariance is at most 1, so we cannot have it's greater than 1. So 95% confidence interval, and things are normal. You remember that y follows multivariate normal, meaning that each individual value of y also follows normal distribution, mean 0, and then the covariance does not exceed 1. So the 95% confidence interval is between two sigmas of the mean 0. So it's -2, 2 will give us the 95% probability. And we get a lot of bumps in this range of between 0 and 10 because short distances are highly correlated and long distances are essentially uncorrelated. All right. And another observation here is that the line is very smooth. And in fact, it's actually infinitely differentiable. And that's one of the biggest, probably, caveats of Gaussian process when applied to engineering problems is you're making a very strong assumption about the relationship between x and y. You assume that relationship between x and y is modeled by infinitely differentiable function, which is of course not always the case. But in any case, although it might not be the true assumption, or the assumption might not be the true fact, but even when it's violated, the Gaussian process actually is still useful and still does produce uh, gives you something that you can apply, and it's good enough. So I'll stop here. It's just good enough in cases when things are not smooth. All right. Okay, so let's draw a few more samples. We're just gonna generate 3 samples now, and we're gonna plot them now. So this is our original black line, and you see a couple more samples. So all of those are just random draws from this Gaussian process with zero mean and covariance function given by exponent of negative distance squared. Okay, but this is not what we really want to do. Generation is of course might be useful, but not typically is the goal of the analysis. A more useful thing would be is to do a prediction. So let's say we have a data set. We're gonna call it dn, and the data set is just n pairs of x and y. So we're gonna call this data set dn. And let's say you give me a new point x, okay, and I want to calculate the value, or I want to predict value of y at this point of x given this data set. So I have training data set, I get a new observation x, I want to predict y for this new value. Typical prediction problem. And sometimes you will hear this word non-parametric model or non-parametric regression. And if you look at the Gaussian process, the only thing that defines the Gaussian process, at least in this simplest case, is the covariance function. So covariance function is the only thing that we need to define the Gaussian process. And covariance function doesn't really have any parameters. So that's why there's nothing to fit here. That's why sometimes it's called non-parametric. Although later we will actually add parameters to it, but we will keep calling it non-parametric because in its simplest form, there are no parameters to estimate. All right, so what we want to do now, we want to predict the value of y given the data set D. And since all of the observations are Gaussian, and so this one is also be Gaussian, so that's goal of going to follow normal distribution. And so let's see how we can calculate this normal. So essentially we need to calculate two things. We need to calculate the mu for this value and the variance. And it actually comes from a simple property of a normal distribution. So let's say you have a variable x, and you can split it into two parts, x1 and x2. And then let's say x follows normal distribution, and with some function mean mu and sigma. And let's say you can split the mu into two parts, mu1 and mu2. So mu1 corresponds to the x1 and mu2 corresponds to x2. So let's say we just have first q parts, the first q elements of the vector is x1 and the rest of them is x2. And now in the same fashion, we're going to split the covariance matrix. So that's the covariance within x1. This is covariance within x2. And then you have sigma 2,1 and sigma 1,2, which gives us the covariance between elements of x1 and x2. All right. So once you've done this, and you know that jointly, so x1 and x2 follows normal distribution, then x1 given x2 also follows normal distribution. And we actually can calculate the covariance and mean of this normal distribution. So here is the conditional. So what we're interested in calculating distribution over x1 given x2. And the mean of x1 given x mu is mu1. So this is the mean of x1 itself. So we take this as a starting point. We start with mu1. And then we take the difference between x2 and mu2. So since we learn already x2, then we're going to use, it's actually essentially what it is. It's a Bayesian update of a multivariate normal. And we talked about Bayesian update for univariate case. That's just a multivariate extension of it. So in this case, you can think of x2 as our data. And we know that the prior for x2 was mu2, so it followed mu2. So we take the difference between those two. And then we weight it. And the weight comes by this, in the Kalman filter, it's called the Kalman gain matrix, or just, just the gain matrix. So it basically tells us how to correctly weight the difference of the residual between x1 and mu2, sigma 1, 2, sigma 2, 2 inverse. And then the covariance of x1 given x2 is, again, we start with the covariance of x1 to begin with, and then we subtract x1 to 1, x2 to inverse, so it's the same gain matrix you see here, and we take sigma to 1 as another term in this multiplication. Anyhow, so we're not going to go through proving this relationship. You actually just can Google multivariate normal conditional, and you'll find a Wikipedia article that gives you those formulas. But an interesting feature of this result is that conditional upon x2, the variance of x1 actually decreases compared to the original one, y11, right? So and that makes sense. So we had something we knew covariance in x1, so that was sigma 1 1, and once we learn something, we actually decrease the covariance. So that's that's very intuitive. But the amount by which it decreases does not depend on the value of x2. It actually depends on the covariance between x1 and x2, whereas the mean is also changes. And the amount by which it changes actually does depend on x2. So the mean of x1 shifts in relationship to x2, and the covariance does not depend on x2. It only depends on the covariance of x1 and x2. And also we know that sigma 1, so this part is symmetric. So sigma 2 to 1 equals to sigma 1, 2 transpose. All right. So now we're just going to use this result to do the prediction using the Gaussian process. And as you could have guessed, if we have observations, our data set dn, and we know that y follows normal distribution centered at 0 and given by covariance matrix sigma n, and then I give you new value x star, and I want to calculate y star, which is actually, let's use star here, star, which is just my prediction at x star. Then what I'm gonna do, I just gonna take, so in my data set I have two parts. I have x1 xn, so that was my x observations. Also have y1 yn. Okay, so I know that y star and y, so the y part comes from the data set, and y star is my value for which I'm trying to predict, will follow normal distribution. All right, and I know the covariance of, so this y22 part, I know I can calculate it using my covariance function of the Gaussian process. And I know my sigma 1 1, so sigma 1 1 is just the covariance of my new x with itself, which is 1. So my sigma 1 1 equals to 1. And then my sigma 1 2 1 and sigma 1 2 here. So those two are just the covariance of new x star with x1 xn from dataset, from my training dataset dn, which I also gonna calculate using the covariance function. So I have everything I need in this, and then the mean, the mu is just 0, so mu1 is 0, and mu2 is also 0. And now I just gonna use my conditional update formulas. I'm gonna update my mu. So you remember I start with 0, so I just don't include it. And it's my sigma times sigma. So that's my sigma 1, 1. That's my sigma 2, 1. And that's my observation yn, the one that comes from the training data set. And the variance is the same thing. I start with variance 1 and then I reduce it by this value. And one thing to note here is that the mu of x is just linear in observations y. So it's just a matrix, although it has inverse here. In the end, it's going to be just a matrix. So mu is linear function in n, or linear function in y, in the training data set yn. And that's the mu, you remember, that's the mu of the y, the new y, the y star. And so we just have a linear predictor. And in fact, that's the best linear unbiased predictor. And now sigma squared is lower than the marginal variance of 1. So we subtract something from 1, subtract some positive number. So we learned something from the data yn. In fact, the amount it goes down is a function of the distance between x and xn. So the closer your new observation to the observations you've seen in the data set, the lower the variance going to be, and vice versa. The further you are away from the observations you've seen, the larger the variance is. It's the same thing. Analogy to it is the nearest neighbor. You can think of it the same way. So the closer you are, the more sure you are about the prediction. The further away, the further you are, the least confident you are about the predictions. But the variance does not depend on the yn values. It just depends on the distances between the x values. And if you want to do multiple predictions, the same thing will work. So you give me a whole bunch of new x's for which you want to predict. So instead of just having 1-by-1 block matrix, I'm just going to have, so let's say you want to predict for n prime new values. You're just going to have n prime by n prime blocks, and I'm just going to do the same calculations. So let's do a simple example. Let's say we have n equal to 8 observations in the data set. And then we'll just x just a sequence between 0 and 2 pi, and we'll try to approximate, or we'll try to model the sinus function. Again, we're just using the simplest covariance function. We calculate the pairwise distance and then take exponent of the negative of those distances. And let's say we want to predict the new values for the new, so those are my new x values for which I want to predict. And they're going to change between negative 0.5 and 2 pi plus 0.5. So we're going to go a little bit outside of the range of the data I've seen in the training data set. So we're going to calculate the distances within this data set, and then we're going to calculate the covariance function, and then we're going to calculate distances between the new values of x and the old values of x. So let's go back here. So that will be our sigma 1, 1. Actually, here we use it, we're gonna call it sigma 2, 2. Sigma 2, 2. So that's the known values, and that's gonna be our sigma 1, 1, and that's gonna be our sigma 2, 1, and sigma 1, 2. It's the same thing. It's just one is transpose of another. And let's calculate the update equations. So we have to invert the sigma matrix, and then we take some matrix multiplication with this inversion. And so sigma, we'll call it sigma p, is the sigma for predictive distribution for the new y's, and then we're just going to generate 100 samples from it, and then we're going to calculate the confidence bounds. So let's visualize it. So we're gonna plot the draws. So remember, we generated 100 draws from the posterior predictive, and we're just gonna draw them in gray lines. So every single gray line is our prediction or sample from the Gaussian process. And Gaussian process tells us what it makes an assumption what is the true relationship between x and y, and we just generate 100 realizations from this probabilistic model. So you see them in gray lines. So those are different samples from Gaussian process. And then the blue line is the mean. So it's actually the true value. X-axis, the sinus of x-axis. So the blue line is the true value of something we're trying to predict. And then x and y, so those are the observations that we used. So this is our data set dn. And then we also plot the quantile lines. The red dotted line is our 90% confidence interval. And the black line is the mu values. Okay. All right. So what do we observe? So one thing is that predictive surface interpolates the data. So interpolates means it is actually exactly the value of the training data set in the observed locations. So whenever we have a point, our predictive line goes exactly through this point. And because the covariance is 1 at the most, and it approaches 1 from the left as x prime approaches x. The error bars have the football shape. They are the widest at locations that are furthest away from the xi, the observed values. And the error bars get really big outside of the range of the data. So if you see here, they actually grow with the square root of t kind of law. And the predictive variance we know will level at 1. So at some point, it actually will flatten out. So it will be like this further away. And the means that it means that we cannot trust the extrapolations. So and model tells us about that. The further we are away from the points inside the training data set, the more uncertain the model is, and the closer you are, the more. So if you try to predict for value, so let's zoom in here, right? So if you try to predict for value here, your error bar is going to be relatively low, and if you try, and you try to predict somewhere here, then your error bars are going to be wider. And the moment you go outside of the range of the data set, your error bars becomes very wide. So if you try to predict somewhere here, that becomes very uncertain. So intuitively, this model makes a lot of sense. It interpolates, it gives you uncertainty bounds, it models things as normal distribution, and then at the end you can not only get the means out of the model, but also the confidence interval or the covariance functions. That's one of the biggest advantages of Gaussian process. It comes with this flexibility, so it can model very complex data sets. So you see, it can easily model sinus function, but it also gives you uncertainty about the predictions.